Yeah.
Okay, everyone, welcome back from the week of the experimental seminar. This week we have Alexey Ovchinnikov, who's going to talk to us about parameter estimation in discrete time systems.
Thank you for having me here. So we will have a interactive seminar today. And I'd like to know a little more about your backgrounds. So could you please introduce yourself, just say a few words, what you're doing, what you're interested in, what your background is.
Sure, should I start maybe?
Yeah, yes, please.
Okay, so I'm Robert Doherty Bliss. I'm a fourth year grad student here at Rutgers. I work in experimental math, and I think mostly about combinatorial problems and things related and how to solve them with computer algebra.
Oh, all right. Who is next?
I'll call on Lucy. Lucy, you go next.
Yeah, unmute yourself and
So we are in the same room, me, Danny, and Natasha. So I'm just gonna talk from Danny's computer. I am a second year at Rutgers. I haven't started research yet, so.
Okay, how about Danny then?
Okay, I'm also a second year here at Rutgers. Also haven't started research, but I'm primarily interested in combinatorics. I think right now more like extremal combinatorics, but suppose that could change. I guess while we're all in the same room, Natasha, do you want to go ahead?
Yeah. Hi, I'm Natasha. I'm also here at Rutgers and also a second year student and also looking for an advisor. And I'm interested in combinatorics, maybe more on the numerative side.
and you can talk Russian to Alexey, I guess, if you.
Yes.
But
not... George?
Hello, I'm one of Dr. Z's students. I'm a fourth year. We do experimental math and some combinatorics. AJ.
Hello, I'm also one of Dr. Z's students and do experimental math. Yeah. I don't know who already went in that because I joined late.
Well, while we're on Dr. Z's students, I'm Blair. I'm a fifth year. I have spent most of my time doing research on Boolean functions. Right now, I'm looking at statistical properties of subcubes of Boolean functions.
All right, so who else is willing to share?
Swihong, would you like to introduce yourself?
Sure. So hi everyone, my name is Yi Hong. So I'm a new new assistant professor in Rutgers, and my research is mostly on enumerative and maybe algebraic combinatorics and a little bit of probability. So nice to see everybody here.
Professor Chan is speaking in 2 weeks in the next seminar.
Oh yeah, yes. Thanks, Daron, for the introduction.
Vladimir?
Okay, go ahead, Alexey, I think.
Right, so let me begin. Okay, so I have a question to you. Let me draw a picture. To the best of my abilities. So what is this? What do you think this is? How would you call this?
Yeah, please feel free to.
Yeah, so please say.
A cube that says whole wheat on it.
Okay, so what else? Any other ideas?
Could be a box of cereal.
So cereal, that's a possibility. What else could be there?
It could be bread.
There could be bread, yes. And what else could be there?
Could be a bag of flour.
Okay, so very good. This one?
No.
No.
F-L-O-U-R.
O-U-R. Okay, let's do that. Let's do O-U-R. Okay, That sounds good. Now, how about this one? What is that?
A spider, maybe.
Uh-huh. And what else could that be?
An ant?
Uh-huh. And what else? Who likes flower?
Could be a flower. Could be a
No.
bee of some kind. Yeah.
Uh-huh. Okay, so very good. So this is okay. Nice. So in this talk, we'll talk about flower beetle equations. And actually, I forgot to open them up on my computer. Can you look them up in the internet and tell me what they are?
Flower beetle equation.
Mm-hmm. Equations. So there'll be
Equations. I'm
several
sorry.
of them.
FLOUER beetle equations.
Mm-hmm.
Flower beetles. It looks like some kind of bug of some sort.
It's a bug that eats flower. In fact, when I lived in North Carolina, I actually experienced them. I left whole wheat for a number of months on the shelf, and I actually got some of them.
So this is a rebus, like a puzzle?
Ask it again?
It is like a rebus. So you're supposed to have a phrase from pictures. It's a puzzle, right? What are you doing?
Oh, yes, we're doing a puzzle, and with the participation of the audience, so they define the equations, tell me what they are, and then we will gonna solve them.
It's a system of discrete equations.
Very nice. Okay, so what are these equations? Can you tell me?
Yeah, it looks like there's three things. There's something called L, something called P, and something called A.
Very good. So one of them is an egg, the other one is a child, and the third one is an adult. So these are the three variables in the equations. And maybe the system that you see has sort of complicated notation. Maybe if you can simplify it while you're telling me, that would be nice.
Okay,
Like
sure.
indices, maybe unnecessary stuff you can remove and tell me what these are. So there are three equations, and what are these equations?
So L, the child, the larvae, L of t plus 1 equals some constant times A of t times e to the linear combination of L and A. Yeah, something like that. So P of t plus 1 is some constant times L of t. A of t plus 1 is P of t times exponential of some constant times A of t.
Times A of t, you said?
A of t. Plus, yeah, outside of the exponential, some constant times A of t.
Sorry, just okay. Times you said A of t?
Yes, A of t.
A of t. Okay. So this is a system of equations in three unknown functions that depend on time. And parameters. These parameters.
It's a recurrence equation or finite difference, a system of recurrences, right?
That's correct. System of recurrent equations. So system of difference equations, of nonlinear difference equations with unknown parameters. And so the parameters, okay, what's going on? Parameters are A, C1, dot C5, unknown. And question is how to find from LPA, LP, maybe LA, and so on. But this is a question.
And what about the other way? If we know them, is it easy? Is it possible to solve these, or do we just have to kind of take them as they are?
Could you repeat your question? I didn't get it.
Does this have like a closed form solution once you know what the parameters are?
Are you asking how I'm going to use the values of the parameters?
Possibly,
Or-
yeah.
Right. So that's a question. I don't know the answer to this question. In fact, so that's a question to biologists who use this. But what I know that in biology, these parameters are estimated from real data on L, P, or A, whatever is given. So whatever in biology lab is measured, maybe the biology lab only measures L and P, or whatever, some other combinations, and they try to estimate what the values of parameters are for some their own investigation purposes. This could be that these parameters also appear in other biological systems. They want to know the value to use elsewhere. They use this one to estimate. And okay, so this is a general question one would like to answer. Now, this is a complicated looking problem. What are the things that make it complicated? What do you think are things that contribute to the complexity of this question?
There are a lot of parameters and only 3 values here.
Right. But what's so good about this, we know them as functions. So we can actually produce many values out of them to iterate. So we measure them at this time and the next time, and next time, and so on. And so I mentioned, I've heard you mention algebraic combinatorics, but what is everything here is in the framework of algebra, or is there something that you see that's more complicated than that in the system?
But it's non-linear, that makes it very complicated. So there's no
Right,
hope for closed form.
Right, so it's not a non-linear system. Yes, it's non-linear, but it's very non-linear. It's not just a polynomial system of equations. It also has an exponential function, which makes it rather tricky to analyze. But now, how do we approach a complicated problem? We break it down into simpler questions and try to answer them. And let's look at a toy example regarding just this question generally. So let's do, suppose we have just one of them. So toy example. L of t plus 1 is equal to A times L of t. Suppose we want to find A from L of t. How do you do this?
Write down an equation if you know the values. Just divide by L of t, I guess.
Yeah, perfect. Yes, so A is equal to L of t plus 1 divided by L of t. Very nice. So we can do this simplified situation. Let's do another one.
Robert, there's somebody else answer.
Huh?
Somebody else besides Robert.
Oh, yes,
is welcome
yes,
to answer.
yes, please.
Okay, I'll mute myself for the next question.
And Natasha, how about you?
We should be able to find A plus B by subtracting L of t plus 1 minus L of t, but I don't know how to find A and B individually.
Very nice. I agree with you completely. And so so our suspicion is, conjecture is, so, well, not even a conjecture, statement that A plus B can be found. So this is L of t plus 1 minus L of t. What about A and B individually? So conjecture is cannot find A or B individually. Why not?
There's no way of separating them.
Well, yes. So this is an intuitive explanation. Can you think of something that's at least sounds a little more rigorous?
Sure. We can express A in terms of B, and B in terms of A, but there's no way to express either A or B in terms of things that are not the other variable, or to combine these equations in any way.
And why not?
We only have one equation and two variables.
Interesting. Okay, let's take a break from this example. Let's do another example. So I leave some space to fill in. And let's do this one. Can we find what do you think?
So this one we can do.
We have one equation and two unknowns, right? But this one we can do.
Yes.
So,
Probably we can do.
So how can we do this one?
Well, if we know values of L, we can plug in two different values of T and get two equations.
You're doing difference algebra now. Okay, so what you're doing this one. We had one equation. With difference algebra can make two, no problem. Put them into a system. And what do we do? We solve for A and B, correct? So what was different in number two? So we're thinking, suppose there is a formula that depends on L of t plus 1, and so on, and B is another formula. So what would go wrong under this assumption?
Well, in equation 2, it's really only one parameter. You just replace it by A plus B. And
right. And so how do you analyze it?
Generate in some sense.
So suppose you're doing experimental math. Could you teach me some experimental math? How do you prove using experimental math that you cannot find A or B?
That you have many A and B's.
Very good. Many A and B's then that do what?
You give the same equation, kind of.
Very nice. That's it. And can you give me some? I like concrete numbers. Can you give me concrete A and B that give you the same answer?
1 and 1, 2 and 0.
Very good. So the answer cannot find because, and here's the proof. 1 plus 1 is equal to 2 plus 0. Do you agree? So this is a proof. Okay, so that's the reason. So
that's one proof out of infinitely many proofs.
Very nice. I completely agree with you. So why are these examples useful to us? They teach different things. And in particular, number 2 is a warning. It tells us that, okay, this is the example, we were able to figure it out. But it's possible that it's embedded in some very complicated situation. And we're trying to estimate those parameters in this complicated system, get an answer using some numerical method. But it could be the case that there is another answer that fits the same data. So this situation, number 1 and 3, go by the name identifiable. So every parameter is identifiable. In number 2, non-identifiable. And this property, whether identifiable or not, is the first thing to check before you jump into parameter estimation to actually find values. And let's work on answering the question of identifiable or non-identifiable first for this model. So for flower beetle, identifiable or not? Now, the answer could depend on what you measure, because when you express it via formula, which one is, I was not using this for a long time. I just wonder, is this? Oh yeah, this is the thing. Okay. Your ability to express a parameter depends on what you put into a formula. And just, intuitively speaking, if you allow more in this formula, that possibly more parameters will become identifiable. And you could have different answers. Once we know for which combinations of measurements we have identifiability, we can go into estimation. Now, in fact, you already developed a technique based on the 2 examples, how you can try and approach this. When we had just one parameter, which tried to represent it as right away as a function of what we measure. For non-identifiability, okay, so we use experimental math. This is something else. To get a positive answer, and here we use differential algebra. And when we difference algebra, how we use that, we apply the prolongation to one of the equations to generate more. And the second step in this approach was linear system solving. How do we solve a linear system? We solve it by Gaussian elimination. So our goal was to be able to express each a and b in terms of the function L. But we didn't want a and b to appear together. They already appear here, but we wanted to see if we can find each of them independent. So when we do this Gaussian elimination, we just want to eliminate some of the variables. And in fact, there is difference algebra with algorithms that can do this kind of elimination for you. We also implement it. But that's true if you begin with polynomial equations. Our equations are not. They have an exponential function. And let's try to decide today whether this is a real obstacle, whether we can do at least something about it. And with what we can do about it, there are still some remaining challenges. So let me ask you, what do you think, how you would approach answering this question? Maybe trying to do this kind of steps, but if you deal with an exponential function. Now here we have a complicated system. It's okay to pick just maybe a few equations and experiment.
Maybe I had a comment, F-solve that numerically solves even complicated equations, numerically, of course, and approximately.
That's very nice, right? And before we go to F-solve, we need to be sure that what it's solving for actually is unique.
Yeah.
So that's the thing, right? And maybe it's F-solve, maybe this is some sort of least square optimization. So whatever that method is, we want to make sure that whatever it converges, it can converge to something meaningful. Maybe it gives you an answer, but the answer would be completely wrong. So, what do you think we can do with an exponential function? Can we maybe,
Try and stick some logarithms in there.
very nice. Good idea. So where would you stick a logarithm?
Maybe say, for example, let L of t be log of some other function.
So for L of t,
Yeah.
so you
Or maybe A of t is
so
a better place to start. Maybe A of t is a better place to start.
A of t is a log. Okay. So let me try to, maybe I'll write over here. Maybe let me just copy that last equation. It was something like, what was the variable? Do you remember? You have it in your computer already, the system.
I do. Do you want the last equation?
Yeah, the last equation, because you're doing A, right?
A of t plus 1 equals P of t times e to the constant times A of t, plus other constant times A of t.
Okay, so let's stop here. Suppose we didn't have the tail. So what you're doing is apply, okay, so A of t is of something of let's do Q of t. Okay, is this okay?
Sure.
Q is okay. Okay, so then what do we have? We have log of Q of t plus 1. And then we have Q of t to the power c, correct?
Yes.
Is this correct? Yeah. Okay. Or maybe, but I think with the log, so I think this is Doran. So no, a talk of mine that has had this component. He had a similar idea, but just slightly different. So he suggested apply natural log to the whole equation. What do we get if we apply natural log? What happens? This is natural log of p, right? Is this looks good? And so c is what? C is Is this okay?
Yeah.
Okay, that's good. So sometimes applying natural log would help. What was the actual equation that we had to deal with? What was plus what was it?
Some constant times A of t.
C, okay, d times A of t. How would we go about this one?
Move the tail over to the left and then take a log.
And that would be really successful if we didn't have the d, right? Because then our d sits inside the natural log.
Right.
But as we can see that taking the log can do a lot of things, except for when we have some obstacles like this. So what we can do about this one? And so you're all doing a lot of discrete things, and I don't know how much exponential function is a friend of discrete math. Well, you tell me. I don't know. Exponential function is a big friend of another thing that I'm doing. But how about you? Are you in good terms with exponential function?
We like it, but maybe not as much as calculus does.
But you still like it. That's a good point of start. So what else can you do with an exponential function?
You can differentiate it.
That's very nice. But that's my stuff. You're stealing that from me. Okay, so what happens if you differentiate exponential function?
But this is cheating. This is a difference equation. This discrete math. It's really cheating.
Yeah. So, but he said differentiate. Okay, let's do what happens if we do we take the derivative. So what's the derivative equal to?
Itself.
Okay, itself, very good. But what do we have here? We have e to the ca of t, right? Something like this. What is the derivative?
So c times the derivative of a times the exponential.
Okay, that's very nice. So if we take the derivative of one of the equations, maybe okay. So let me highlight this equation. Oops, I'm so very sorry. Okay, so very nice technology. Okay, I like this. We take the derivative. Then what happens? We can take the derivative of the whole thing, right? Apply the product rule.
So how do you know it's differentiable? This A of t.
Okay, you're asking that's too complicated question. I don't want to answer it because I have no idea. Because I'm lost in the methods and you're trying to take it away from me. Don't do that. Okay, so I do what? See, let me try just not to think too deeply. Okay, e to the ca of t plus d times a prime of t. Okay, so it's a new equation that we created. We had our box equation in the first box, and let me do colors. Okay, let me do. I didn't change anything, so I didn't click, I guess. Okay, so we get another one. So we now have two equations. What do we do about the new equation? It still has exponential functions. And what do we do in math if we have something complicated? What do we introduce for something complicated?
You linearize.
That's right. If we have no idea what this is, we introduce it a name to it, right? Like exponential function, maybe we have no idea what it is, but we give it a name. We call it e to the x. That's what we did. And then we convince ourselves we can actually solve an equation because we just gave a name to its solution. Okay, and let's just give it a name. And what name do you like?
Z.
Alexey.
Yes.
Alexey.
Oh, that was the name. I thought you were referring to me. Okay. So which one, Z or Alexey? Which one do you prefer?
Okay.
If you want me to finish the talk on time, let's use the Z because it's shorter.
Z.
Okay. So then let's call, what do we call a Z? The thing that we want to get rid of, right? So let's call this as a Z. And what happens then? So we have a prime of t plus 1. This is our new equation. It's p prime of t. Yeah, but do I really need that? I don't think so. Let me just go back to the original equation we struggled with. This is a of t plus 1 is p of t. Now, this is e to the cat is z of t now. Isn't this nice? It's gone. The problem is gone, right? Are we done or we need to do something more? We just replace this in the LPA system by z of t and we say we're done? Or do we need to
z depend on the parameters?
Right. Okay, so we need to say what z is, right? And this is the equation for z, this one. Let's use it. So we say z prime of t is equal to ca prime of t times z of t. Really good looking, right? You had one equation with an exponential function. We replaced it with two equations. Okay, one more variable, but with no exponential function. Okay, and I'm very sorry to all of you that this is no longer fully discrete math because it has a derivative in it. So sorry
Whenever
about.
saying discrete math, it's formal derivative. You can think of it as a formal derivative. So it's
Okay, okay. So you forgive me. Okay, so we're still in the. You don't kick me out of the seminar yet. Okay, that's
And
very nice.
That's a mix, right? Differential equation.
Right,
a system.
and they go by a special name. They're called delay equations. Delay differential equations. So now I view them. Okay, so I like differential equations. I now view them as differential equations with an automorphism acting on the variables. So there is a shift. So I now think of them as differential equations. And now, so I have our original system with 3 unknowns, and we introduced the new variable for this one, right? And we also introduce, depending on your taste, maybe you can call this another new variable w of t, or you can break them down in 2 pieces and call each, give each a new name. And for each such introduction of exponential function, you will introduce a differential equation, right? So you would get a system with, instead of, let me, I don't have, I really need your help. So we have, so that you have it all in front of you. Can you help me with the other equations? What was the middle equation, the simple one?
P of t plus 1 equals some constant times L of t.
Okay, A, B, C, D, okay. Okay, so I can decide, I use A, okay. Times what, L of t?
L of t, yes.
Okay, very nice. So we don't do anything about this one. And the first equation.
L of t plus 1 equals some constant times A of t.
It's equals what?
Some constant times A of t.
A of t times
E to the linear combination of L and A.
Very good. I call it
Or
like
W.
that. And now, can you tell me what the derivative of W is in terms of W and everything else? Can you tell me what is in what I'm missing in the parentheses?
So take a derivative of the second equation and then solve for W prime.
Yeah, for the so we have this one. Everybody should know what's going on. Let's denote this by a W. Denote this by a W. So what's the derivative of W? Like the same with the Z.
Yeah.
It's like C1 times what?
Times L prime.
L prime. Okay, sorry about that. It's L prime.
And then C2 times A prime.
Very nice. So we were trying to answer the question, trying to simplify it, but it became, on the one hand, simpler, on the other hand, more complicated. Because we have now 5 equations, 5 unknowns, 5 functions, and unknown parameters. Now, when we do such transformations, I think we should ask ourselves, we ought to ask ourselves, are we now solving the same problem? Or are there some kind of issues when we make such a substitution? What did we do? We replaced the exponential function with a differential equation, defining it. Is this a fully, you think, legitimate thing to do?
If you exponentiate a real function, then it's always positive. So there could be an issue.
You said, no, Would you repeat this again? I didn't. I
When you
didn't fully understand.
exponentiate a real valued function, it has to be positive. So maybe you lose.
Ah, okay, right. So from that perspective, sort of we lost that control, right?
Yeah.
Okay. So if we add that condition that everybody here is positive, is this okay now?
Looks okay to me, but maybe not.
Uh-huh. So if we, let me ask this question. If we solve the differential equation, can you please solve this?
Constant times e to the something.
Oh, very nice.
Initial conditions, maybe that's fine.
Yeah.
Precisely. So we lost that one. So you see, for instance, when we, where was it? Okay, it's here. Oh, it's here. Very nice. So you see, for instance, here, so we have this exponential function we're getting rid of. And we have an unknown parameter. With the replacement using differential equation, what happens to this unknown parameter? It's kind of this exponential function is very hungry function. It eats this unknown parameter. Because when you replace it with just with a new variable w, when you don't specify initial condition, it includes the exponential function and all its scalar multiples. So when we make that such a replacement, forget about a. This system, this new system, as you can see, potentially is not equivalent to the original one. But we can see that the problem is just one-sided. If you already, with this ambiguity for the exponential function, can recover all the parameters, then when you go back to the original one, you can surely recover them all as well. When you make a conclusion from this new system that, okay, some of the parameters we don't know, we're not sure whether we can recover, maybe going back to the exponential functions and resolving the ambiguity with the rescaling, we will be able to recover it there. So the warning, this is not if and only if, but it's still quite good. So let me tell you now, so after this transformation, the next steps is to just do computation. And so the next step is come up with a clever way to do elimination. When we deal with differential equations only, there is already a set up machinery for this. One that kind of doesn't have to think too much. When we deal with differential equations, it's still sort of with trial and error. I've been analyzing these equations with the two collaborators of mine, with Sonia Rueda and Antonio Jimenez Store. And so I can show you some preliminary results. So there are good news that if you know everybody, then you know everybody. So if you know L, A, and P, then you can find all of the parameters. So the answer is yes. For some of the combinations of L and P and A, just picking pairs. For some pairs, we can we have sort of decisive results, almost complete, but they still the remaining challenge is still to overcome this ambiguity of the exponential function for them. For some of them, for some of the pairs, we can't even finish the elimination because it's just getting too complicated.
So there was a system of equations of interest in real life for real biologists. It's not just a made up.
No, this is in real life, interesting for biologists, and the parameter estimation problem there is a really interesting problem.
But the method you develop could probably be useful for other cases, probably. Right?
That's right. That's right. So this is, I just use it. Okay, it has a nice name. It's used interesting for biologists so that you can participate, search for the equations in the internet and so on. That's all how it was staged for that particular purpose. And the message for the algebra here, okay, if we can get rid of the exponential function, we still have some obstacle to go back, but the algebraic system that we get when we're trying to eliminate here variables is really huge, unless you know L, P, and A. And just finding interesting ways of approaching it is a challenge.
In what sense do you know the parameters? Is it, if you know L, P, and A, you can literally write down an equation that tells you what the parameters are, or is it something more complicated?
This is a very good question. I really like your question. So it depends. So here, when we do, where was my, okay. The two example, I'm searching for the two example. Okay, so this is the two example. So here, when we solve for A and B, we just, Kramer's rule apply, you get a formula, right? And you can use that to find the actual values. Now, thank you for bringing this up. If we are able to stay within difference algebra without getting rid of exponential functions and somehow answer this question, we might be able to come up with a formula that is used in real practice to estimate. That will be very nice. What do we lose when we go to differential algebra? This is a very good point. When we get to derivatives, we might still be able, if we are able to identify, if the parameter is identifiable, then we can find also a formula. But the problem with that formula, that it will contain not only functions and shifts, but also their derivatives. When it contains derivatives, biologists will hate you. Because when they have biological data, estimating derivatives, no way. So
we can find an answer, but they're not happy with it.
It's yes and no. The answer that we'll provide will be from the Boolean perspective, yes or no, identifiable or not identifiable. And then we'll give them a green light to use some numerical techniques to actually find values. So if we are to use derivatives, then we step back from using formulas to find parameters. We just outsource it to numerical solving with the certainty that the answer is unique. So that's what we want to establish. If we're able not to go to derivatives, then it's a double win situation, because in that situation, we also give them a method to finding the values. And this is a challenge to to the community to pursue both and see what you end up with. I thank you for your attention, for your participation. That was it.
Everyone, please thank Alexey.
Yes, thanks for a great talk. So this Robert, please end the formal part. But people
Okay, this ends the formal part of this seminar. So I'll stop recording now, but we'll stick around.
Yeah, Alexey, that was really interesting. So I have a question about